Hello, everyone, and welcome. My name is Aaron Smith. I'm the CEO of the Energy and Environmental Building Alliance, and I'm really pleased to present Dr. Tanveer Khan with the University of Central Florida in the FSEC Energy Research Center. Today, Dr. Khan is going to be presenting on approaches for effective, sorry, I can't read, there's a little blockage in there. Approaches for effective isolation, space control, to minimize airborne transmission of contaminants in residential homes. And we were just talking offline as we got prepared for this, that we thought maybe we had missed with this research the window for this important data, but I think now it's more important than ever. I think there are EBA members around the world that will want to absorb this data and understand it. We will be taking questions. So there's a Q&A section at the bottom of the screen. Just enter your questions there. If it's easier for you to put them in chat, enter your questions there. And we'll be taking those today at the close of the presentation. Dr. Khan, welcome.
Thank you, Aaron, for the introduction. Happy to be here to be sharing the results of this study. So in order to better play the video, I'm going to turn off my camera at this point. Hello, everyone. Thank you for your interest in this webinar. I'd like to thank EBA for giving this opportunity to present this webinar today. I'm Tanveer Khan, a postdoctoral associate at the FSEC Energy Research Center at the University of Central Florida. Today, I'll be talking about approaches for effective isolation space control to minimize airborne transmission of contaminants in residential homes. I'd like to acknowledge my co-authors, Charles Withers, Nicholas Bonilla, and Eric Martin for their significant contributions in this study. The funding for this study was provided by the Residential Buildings Integration Program within the U.S. Department of Energy. And the funding to prepare this presentation was provided through an NREL subcontract for technical assistance to EBA. Aerosols containing virus particles can be directly inhaled from the air. While large respiratory droplets fell quickly to the ground, the smaller ones can remain suspended in the air and undergo long-range transmission in indoor environments. For respiratory viruses, including SARS-CoV-2, mitigation of aerosol-based transmission is critically important to protect occupants in shared indoor environment, such as in existing single-family houses. This figure shows three primary transmission routes of SARS-CoV-2: direct contact, indirect contact, and airborne. Because the smallest virus particles or aerosols containing viruses can remain airborne for hours and travel long distances, building ventilation plays an important role in potentially reducing spread of the virus and lower the risk of exposure. This important role of building ventilation is also emphasized by ASHRAE, as it states that transmission of SARS-CoV-2 through air is sufficiently likely that airborne exposure to the virus should be controlled. One of the primary examples of control includes changes in the operation of HVAC systems in buildings. In the US, negative pressure airborne infection isolation rooms are commonly used in healthcare facilities for patients with airborne infections. However, the concept of negative pressure isolation space for residential homes was yet to be explored. The primary objective of this study was to systematically test the effectiveness of various strategies to mitigate potential airborne transmission of infectious aerosols in a manufactured single-family laboratory house under various HVAC operating scenarios, intervention measures, and utilization of exhaust or window fans for pressure control. Now let's watch a short video on this study. After the video, we'll go into the more details. If a person in my house is infected with a virus, how can I prevent it from spreading? If an infected person remains in a separate room, can we consider that effective at preventing other occupants from being exposed to an infectious disease? Let's use an example, assuming the master bedroom is used as an isolation space where a sick person is emitting viral particles in the isolation space. The door between isolation zone and main zone is open. Windows in the isolation and main zones are closed. Central heating and cooling system is on. The isolation zone supply and return grills are open. Under this scenario, there is no pressure differential between the isolation and main zone of the house to contain the virus particles. As a result, virus particles or aerosols containing the viruses will gradually transfer into the main zone through the open door and ductwork of the heating cooling system. This base case shows a worst case scenario where contaminants are not contained in the isolation zone and likely to undergo transfer from the isolation to the main zone. Now, using the example of this base case, let's impose some simple, low-cost controls and interventions to improve containment in the isolation zone by taking the following steps. Keep all windows in the isolation and main zone closed. Close the door between isolation and main zone. Seal off the supply and return grills in the isolation zone. Sealing off the supply grills helps create adequate depressurization in the isolation zone, while sealing of the return grills prevents virus particles from getting transmitted from the isolation to the main zone. If the master bedroom has an attached bathroom with an exhaust fan, run the bath exhaust fan at high speed setting. These steps would create a depressurization in the isolation zone, adequate for containment if the exhaust fan has sufficient flow. To determine if the flow is sufficient, while standing on the outside of the door that separates the isolation space from the rest of the house, hold a piece of tissue paper near the door undercut. If the tissue paper is pulled into the isolation space, the bath exhaust fan flow may be deemed sufficient. If not, additional options could be considered to improve containment, such as install a portable window fan rated at a minimum of 300 cubic feet per minute in one of the isolation zone windows so that it blows air out of the room. Use a portable room air conditioner with the exhaust duct installed in one of the isolation zone windows. While a portable air conditioner can be more expensive than a window fan, this method could be useful in addressing any comfort issues caused by sealing off the supply grills in the isolation zone, which is a key requirement for adequate depressurization and a strong containment. However, a situation can occur where there is no window in the isolation zone and the bathroom exhaust fan may not be delivering high rate of airflow. In such cases, we could still keep the bathroom exhaust fan running and install the portable window fan in the main zone as a supply fan, meaning it will be blowing air into the main zone. The resulting effect of this control strategy would create adequate depressurization and strong containment in the isolation zone. In the next few slides, I will briefly discuss methods including the following topics: site description, measurements and monitoring of air tightness, airflow, pressure differential, environmental parameters, isolation zone containment testing, and test configurations and cases. The experiments were conducted at the FSEC Manufactured Housing Lab, which was an approximately 1,600 square feet home with 3 bedrooms and 2 bathrooms, with unvented and unconditioned crawl space, vented attic, and wood frame walls. The house air tightness was roughly 5 ACH 50 with respect to outside. This figure shows a generic layout of the test site. As it can be seen, the master suite, shaded in pink, was used as the isolation zone, while rest of the house served as the main zone. The solid green and open red circles denote locations of the air quality monitors used in this study. In this study, we used fine particulate matter or PM2.5 as a surrogate for virus transmission. PM2.5 are particles or aerosols that are smaller than 2.5 micrometers in diameter. PM2.5 was generated using an oil based diffuser placed in the master bedroom. This figure shows the master bedroom or the isolation zone with the aerosol generator and the PM2.5 monitors. We conducted air tightness and airflow measurements and also monitored pressure differential and important environmental parameters. For air tightness, multi-point tests were performed using an ASTM standard test method. Guarded and unguarded tests were conducted to determine leakage between zones. We used both passive flow capture hood and powered flow capture hood method to measure airflow from bath exhaust fan, supply grills, portable window fan, and portable air conditioner. Pressure differential between isolation and main zone and between main zone and outside was monitored in real time using manometers at 10-second intervals. Pressure differential data were converted into 15-minute average for all calculation purposes. Indoor and outdoor temperature, relative humidity, wind speed, and directions were also monitored. Three major steps were involved in evaluating isolation zone containment. First, we generated PM2.5 in the isolation zone. Supplementary measurements were performed by injecting sulfur hexafluoride in the isolation zone. Secondly, we measured PM2.5 and sulfur hexafluoride concentrations before, during, and after an intervention. These measurements were conducted both in the isolation and main zones using multiple research grade and low cost monitors. Using the measured concentration of PM2.5 and sulfur hexafluoride, we calculated their concentration ratios between the zones. Finally, we monitored pressure differential across zones. Pressure differential was used as the primary metric for evaluating containment potential of isolation zone with respect to the main zone. For all tests, our target differential pressure value or DP in the isolation zone was minus 2.5 Pascal or greater depressurization. The threshold of negative 2.5 Pascal was based on ASHRAE standard 170. The test cases and configurations were developed based on various HVAC operating scenarios, intervention measures, and primarily utilization of bathroom exhaust or window fans. Interventions involved closing the door between main and isolation zones, closing or opening the windows in the isolation zone, sealing of the supply grills in the isolation zone. In total, 17 case scenarios were developed and tested, where each test was repeated 2 or 3 times. This table lists all the 17 cases with case specific details. For example, in case 5, the door between isolation and main zones was closed. Isolation zone bath exhaust fan was on. Window fan was not used in the isolation zone. All windows in the main zone were closed. Central heating and cooling system was on, and isolation zone supply grills were sealed off. The figure on the left shows a portable window fan installed in one of the isolation zone windows so that it blows air out of the room. The figure in the middle shows a portable air conditioner unit with the exhaust duct installed in one of the isolation zone windows. However, a situation can occur where there is no window in the isolation zone and the bath exhaust fan may not be delivering at high rate of airflow. In such cases, we could still keep the bathroom exhaust fan running at its highest speed setting and install the portable window fan in one of the main zone windows as a supply fan, meaning it will be blowing air into the main zone. The resulting effect of this control strategy would create adequate depressurization and strong containment in the isolation zone. This fan configuration is shown in the third figure. Some important features of the test cases are listed in this slide. All our tests included a baseline period where an intervention or a control was not applied. We kept the door between isolation and main zones closed with a combination of the following: bath exhaust fan on or off, central air on or off, supply grills in the isolation zone open or sealed off, windows in the isolation and main zones open or closed, and low cost window fan installed either in the isolation zone or main zone. In addition, we have also tested the effect of simulated door opening events on isolation zone containment potential. But keep in mind, the primary objective here is to create a negative pressure differential of 2.5 or greater in the isolation zone with respect to the main zone. Now I will talk about the results starting with the airflow characteristics. This table shows measured airflows for bath exhaust fan, window fan, supply grills, and the portable air conditioner unit. At high speed setting, the bath exhaust fan flow was measured at 110 CFM, and at low speed setting, the flow was measured at about 50 CFM. The portable window fan, which was a 9-inch twin fan, moved air at over 300 CFM, while the single speed portable air conditioner unit was capable of moving air at about 230 CFM. This slide summarizes results of the best and worst isolation containment cases. As you can see from the table, 4 cases are listed as best cases and 4 cases are listed as worst cases. The determination of best and worst containment cases was primarily based on isolation zone differential pressure or the DP value with respect to the main zone. As you can see, for all the best cases, the average differential pressure values exceed the threshold of negative 2.5 Pascal. And for all the worst cases, the DP values do not meet this threshold. So, in summary, for all the best cases, the door between isolation and main zones was closed. Windows in the isolation zone were closed. Windows in the main zone were closed. Central heating and cooling system was on. Supply and return grills in the isolation zone were sealed off. And for all the worst cases, the isolation zone door was open. Windows in the isolation zone were open. Central heating and cooling system was on while we left the isolation zone supply grills open. This figure graphically shows the results described in the previous slide. The x-axis on this graph shows the case numbers. The primary y-axis shows the concentration ratios between main zone and isolation zone for PM2.5 or sulfur hexafluoride, which is denoted as Tg in this graph. And the secondary y-axis shows the pressure differential values. One important highlight of this graph is for all strong isolation zone containment cases, which are cases 4, 5, 6, and 17, the mean differential pressure in the isolation zone was at or well below the benchmark of minus 2.5 Pascal. The ratio of measured PM2.5 or sulfur hexafluoride concentrations between the main zone and isolation zone is also useful in differentiating the best cases from the worst ones. For an effective containment, Mz over Iz values for PM2.5 or sulfur hexafluoride, in this case Tg, should be close to zero, meaning during an intervention there was little to no transfer of contaminants from the isolation to the main zone. As you can see from this graph, for all the strong cases, these concentration ratio values are much smaller than the values obtained for the worst cases. So to create adequate depressurization in the isolation zone, in case 4, a window fan was used. In case 5, a bath exhaust fan was operated at high speed setting. In case 6, bath exhaust fan was operated at high speed setting, while the portable window fan was used as a supply fan in the main zone. And in case 17, a portable room air conditioner with the exhaust duct installed in one of the isolation zone windows was used. Recall that we used PM2.5 as a marker for virus transmission. Now let's take a look at a few examples of PM2.5 time series for a base case as well as for strong and weak containment strategies. This figure shows the time series of PM2.5 concentrations for case 1, which is a base case. In this case, the door between the isolation and main zone was open. Central heating and cooling system was on. Isolation zone supply grills were open, and neither the bath exhaust fan or window fan was used for pressure control in the isolation zone. In this time series, PM2.5 concentrations are shown in the primary y-axis, while the pressure differential values are shown in the secondary y-axis. The red line in this graph denotes PM2.5 concentrations in the main zone, and the green line denotes PM2.5 concentrations in the isolation zone. The blue squares denote the pressure differential values in the isolation zone with respect to the main zone. The time series plot can be divided into 4 panels. Background when the diffuser was off, followed by a period when the diffuser was on but there was no source control in the isolation zone. The third panel shows the intervention period when we opened the door between the isolation and main zones while the diffuser was still generating aerosols in the isolation zone. And the fourth panel shows a period where the diffuser was turned off and the isolation zone door was left open. From the third panel of this graph, one can see the main zone concentrations were nearly 30 times higher than the background concentrations. This indicates that aerosols generated in the isolation zone transferred through the open door and the ductwork of the heating and cooling system. This case shows a worst case scenario where contaminants are not contained in the isolation zone and likely to undergo transfer from the isolation to the main zone. This figure shows an example of a strong containment strategy. Case 5 is one of the best cases where depressurization in the isolation zone was created by using the bath exhaust fan running at high speed setting. One can compare the PM2.5 concentrations between zones for a given panel. For example, in the second panel, PM 2.5 concentrations in the isolation zone were substantially higher than the main zone concentration. In the third panel, when the bath exhaust fan was turned on, the concentrations in the isolation zone dropped rapidly, while the concentrations in the main zone remained at or similar to the background level, which indicates that contaminants were strongly contained in the isolation zone. The pressure differential value shown in blue squares also support this finding. This figure shows an example of a weak containment strategy. In case 8, the door between isolation and main zones was closed. Bath exhaust fan was on, central heating and cooling was off, and one of the isolation zone windows was open. As you can see from the third panel of this graph, the PM 2.5 concentrations in the main zone increased by a factor of 20 as compared to the background concentrations measured in the main zone. This finding suggests that interventions using open windows may not provide adequate containment in the isolation zone. So, for an effective isolation zone containment, we need to use either a bath exhaust fan or a portable window fan, or we could use both. Keep in mind, we must block the supply and return grills in the isolation zone for adequate depressurization and strong containment. So, in summary, this study was solely focused on ways to limit airborne transmission of contaminants using relatively simple efforts that utilize existing or easy to acquire materials and simple processes. We identified 4 strategies having the most potential for strong containment in the isolation zone. Of these 4 strategies, 2 involved using bath exhaust fan and low cost portable window fan as an exhaust fan in the isolation zone. Use of a portable room air conditioner with the exhaust duct installed in one of the isolation zone windows provided strong containment. While a portable air conditioner can be more expensive than a window fan, this method could be useful in addressing any comfort issues caused by sealing of the supply grills in the isolation zone, which is a key requirement of adequate depressurization and strong containment in the isolation zone. Based on our study, we provide the following major recommendations. Locate an infectious person in a room with a closable door. Placing them in a master bedroom with an attached bathroom that has an exhaust fan will help limit exposure. The door between isolation and main zones must remain closed at all times except for occasional opening and closing as needed to tend an ill person. The isolation zone supply grills should be sealed off. If there are return grills in the isolation zone, they need to be sealed off as well. In addition to bath exhaust fan, a portable window fan can be very useful in creating adequate depressurization in existing homes. Keep in mind, these recommendations were developed primarily based on achievement of pressure differences that deemed sufficient to improve containment. As no testing was done with actual infectious aerosols, there is no guarantee that containment will completely prevent disease transmission. For more details about this study, here are the links to the technical report and the fact sheet. And also, we recently published a peer-reviewed journal article um, where we tested few of these control strategies in a real house and found promising results. For any questions, comments, please feel free to contact me at this address. I hope you enjoyed the presentation, and I'll be happy to answer any questions that you might have at this point.
Great. Thank you, Dr. Khan. There we go. We've got the email there for everybody. It's tcon@fsec.ucf.edu. We can open it up to questions that anyone has. If you want to put that in the Q&A section or the chat. I have a question. We talked about this briefly as we were coming on. Did you test any of the air purification, air filtration systems? And if so, is there any efficacy there to that strategy, or was that not tested in the study?
No, we haven't tested any air purification systems in this study. However, there are other studies that have looked into the efficacy of such air cleaners in reducing pollutant concentrations, not specifically virus particles, but in general, you can assume that virus particles, given their size in the micrometer ranges, the air purifiers with filtration systems, they should be effective.
Mhm. Great. And did you test humidity control? I mean, we hear a lot about the humidity control being important in the house to knock down the virus particles, but was there any test at different humidity levels within the house?
So I want to stress that the method we used in this study, we used fine particulate matter, which are not real virus particles. So trying to correlate the effect of humidity on actual viruses is not the scope of our study.
Right.
But there are other types of studies out there that specifically looked into different viruses and how they interact with different RH levels, whereas our study is more focused on containment.
Right. Well, I think it's great strategies, great advice, very thorough study on what to do. And again, to learn more, you can go to the NREL case studies that you mentioned.
Mm-hmm.
You can contact Dr. Khan, and we will have this video available up at the EBA Academy for anyone that you want to share it with as well. And then Dr. Khan, is the presentation available on your website as well?
Not yet, but we could make it available.
Okay. We'll have it up at EBA Academy, but check in for at the FSIC website as well. Well, Dr. Khan, I want to thank you so much for this incredibly educational presentation and for sharing the results of your study with our audience.
I really appreciate this opportunity, and thank you so much for inviting me.
Great.